Hi everyone, this is Introduction to Chords, which is a continuation of our lessons on circles from Chapter 10. This is Lesson 10.2.1. Some prior knowledge that you need to have, and probably most of you have at this point, is just what a circle is, and a couple of basics, which are the radius and diameter. So I've already labeled these. Here's two examples. From the center of the circle to the edge is what we call the radius. And from one edge to the other side, another edge that goes through the center, has to go through the center, we call the diameter. And so since it goes through the center, this is actually a radius and another radius stuck together. So if, for example, radius happens to be x, diameter would be 2x. The whole distance would be 2x. All right, so that's the relationship between radius and diameter. All right, so what we're looking at are chords, and I'll give you some definitions of that in a minute. This lesson starts off with kind of a big real-world problem, looking at perhaps trying to figure out how wide a tree is, but imagine we don't actually have the whole tree, but we have only a piece of it, some fragment of it. So how can we figure out the diameter? How wide is this tree if we don't even have the whole tree to measure, right? And perhaps the tree is way too big for us to measure as well. So can we find the center of a circle if we only have an arc? So if I take this portion of it, just this arc, like maybe it's the bark of a tree, and this is, if I copy it over here, I have this arc which we'll call AB. So if I only have the arc, can I figure out where the center of the circle is? Is it here or is it back here? So can I somehow figure out where the center is so that I could kind of guess the rest of the circle? All right, so that's kind of what we're going to be looking at moving forward. All right, so the next problem, I've kind of just summarized some info that you need to know. I think it's a little bit easier just to kind of see it written out for us instead of reading through a long problem. So the first couple things that we're going to look at is what is a chord. So here's a definition of chord. Keywords here, vocab word that you need to understand. So a chord is a line segment, so it's just a line that connects the endpoints of an arc. All right, so we talked about an arc earlier. So here in this picture I have arc AB. So A and B are the endpoints of the arc. If I draw a line that connects those 2 points, we call that a chord. So you'll notice here I wrote chord AB. This is the one I highlighted in blue. Chord AB of arc AB. You'll notice the straight line on top of the AB. This signifies a line segment versus the arc on AB. That tells us we're talking about the arc. All right. Second part to this is the relationship between the diameter and the arc. So if we have a diameter, let me move this over. All right, so the diameter, in this case, diameter is this line here that's going straight up and down. When it's perpendicular to another chord, so another chord would be this line here going across. So when these two intersect and they form a right angle, they're perpendicular, this diameter bisects, keyword here is bisects, the chord. So it means it cuts it in half. So these two segments are going to be the same. And then it also bisects the arc. So however long or whatever measurement this arc is, it literally cuts it in half. So these two portions are going to be the same. All right, so those are some properties that we get to use when we're working on bigger problems. All right, so definitely good things to have in your notes. The third thing mentioned in this problem is the difference between a major arc and a minor arc. So when we look at a full circle, in this case, this one given to us, when we talk about a major arc, this is the arc that takes up the majority of the circle. So majority meaning most. So when I talk about major arc, I'm talking about the larger of the two. You'll notice there's two arcs here, a large arc and a small arc. So the smaller one we call minor, which takes up the minority of the arc. So small one we call minor arc, large one we call major arc. But if we still label them the same, we wouldn't be able to tell the difference. So you'll notice with the minor arc, we use the two letters, A to B, but with the major arc, I use three letters. This tells me that when I go from A to B, I better make sure I get to D first. So there's no way I cross D unless I go this other way. A, D, B, which tells me this is the major arc. So that's one way to help you identify a major arc is to use the three letters. Three letters wouldn't be necessary for a minor arc because one, there is no letter in between. Even if there was, it wouldn't be necessary since it is a minor arc. So if for some reason these two are the same size, if minor arc and major arc are the same size, means technically there is no major or minor. They would be identical, which means they would take up half of the circle and they both would be 180 degrees. All right, we'll talk about measurements more a bit later. All right, so another thing to kind of have in our tool belt is how can we find the center of a circle. This kind of relates back to the tree problem. I've kind of already started one of these, and then I'll explain it and then try to demonstrate it again. So how can we locate the center if all you have is two chords? So I was given two chords. So in case, let me move this out. Oops. Let's move this. So if I move this out of the way, we have, oops, let me delete this. So this is what I had before. So I'm trying to figure out where the center is without just guessing. So what I did was I started with, if we could actually measure it, if I measured this line and I figure out where the middle is, if I could draw in a line that's perpendicular, 90 degrees, and on the other line, I also figure out where the middle is, and I draw a line that's perpendicular as well, you should notice that there's an intersection point. So these lines actually intersect right at the center. So, which is what I did. I identified the center, and then I drew a circle. With that as a center. And you should notice the circle crosses all the endpoints of those chords. So those chords don't intersect on circle Q. You'll notice these chords intersect. How can we do it on these? Well, it's pretty much the same method. See if I could do this one. So I'm going to look for the middle portion of this line. So somewhere around here. So I'm going to approximate, since perpendicular is going to be somewhere around here. And then I'm going to approximate the center is probably here, make sure it's perpendicular. So you should notice they intersect, which gives me a center of the circle. So I should be able to sketch a circle that goes through, hopefully this works. Alright, not too bad. Alright, so hopefully, so that looks pretty good. So here we have the center of the circle, and you'll notice all the endpoints happen to land right on those. Alright, so these other lines are just, I'll delete those. Alright, and there you go. So there is a way to figure out where the circle is. So if we have the bark of a tree, then technically we could figure out where the center is and figure out how big that tree is. And then once we know how big it is, we could figure out the diameter. Alright, so that's kind of what we're trying to do there. Alright, the following question, this is a good test question that pretty much comes up every year, is here's a circle with a chord given to us, in this case WX. Some notation you need to be familiar with is circle with center Z. So you'll notice it has this circle with a dot in it. That means circle with center. Circle with center Z. Alright, so Z would be the name of the center. So you'll notice in this picture I have Z as the center. Alright, so they give us the length of WX, which in this case is 8, and the radius of the circle is 5. So you should notice there is no radius drawn in the picture. So this is an example where you would have to draw your own radius. So you have your choice of really where you want to put it so that it helps us. Some people might put it here, or traditionally put it here, or maybe want to connect it to one of these other points, or maybe somewhere else. So we place it where we think it might help us. So if I look at the question, it's asking us how far from the center is the chord. So I'm trying to figure out how far is this chord from the center. Well, what's the short, and we're looking for like the shortest distance. So what's shorter, from here to here or from here to here? Right, so notice these two that I'm comparing. It's like, well, if you notice, I've actually created a triangle. So what I'm going to do is I'm going to zoom into this. I'm going to add the radius. So in this case, the radius is 5. But you'll notice earlier I put in this other line. This is really what we're trying to figure out, is how far is this distance. So if it's perpendicular, you should notice that's a right angle, which means we have a right triangle. So the nice part about these circle problems is really they're just triangle problems. So if I get rid of the circle, it's just a triangle problem. Alright, so given the information we have, if WX is 8, if this whole thing is 8, then that must mean the half of the distance is going to be 4. So I'm going to put, let's say this is a 4, and this is a 4, which the other one I don't care about. So if I'm trying to focus only on maybe this triangle, and I'm trying to figure out the measurement of this side. Oops, I don't want to use X. Let's do Y. Alright, so I have a triangle. If you think about it, really I just have a triangle that is I have a 5, I have a 5, and I have a 4. The question is, what is the third side? All right, so you might recognize that as a 3, 4, 5 triangle using Pythagorean theorem, or maybe use Pythagorean theorem to work it out. 4 squared plus 4 squared plus y squared. Oops, those don't look good. 4 squared plus y squared equals to 5 squared. All right, so if we saw this, y will equal to 3. All right. So then how far from the center is the chord? We would say it's 3 units. All right, so this circle problem really just became a right triangle problem, a Pythagorean theorem problem, which, like most circle problems, end up being not really circle problems. And that's pretty much it for the lesson. I'm going to do one more problem, but the next problem comes from the review preview. Review previews problems 53 to 60. As usual, everything else is a good review of prior topics. The first problem is a circle problem that I think is good to do. I like to always do these with everyone. So let's go over this one, which is a good example of other topics we've seen before. So right off the bat, I'm just going to throw out this idea of circle problems are really just triangle problems. So if I get rid of the circle, you'll notice there's kind of just like a triangle with an exterior angle on it. So if I put this back, so let's look at the information we have. So if measurement of angle A is 35 degrees, so if I say this angle is 35 degrees, what is the measurement of CBD? CBD. So we're looking for this angle. All right. So how do these two angles relate? So if I think about what we know about circles, we know a radius is always the same measurement. So technically all three of these sides are the same measurement. More importantly, these two are the same, which means we have an isosceles triangle, which means if this is 35, then this one must be 35. So if I use that information, if this is 35 and this is 35, there's a nice connection between these two angles and the exterior angle. Right? So this exterior angle sum theorem says the two remote angles add up to give you the exterior. So technically, if I add 35 and 35, it will give me the measurement of this angle. All right, it's that easy. If you couldn't figure that out, you could always figure out this angle, which would then be 110. If this is 110, then a supplementary angle would be 70 degrees. All right, so that's another way you could do it. All right, so using that information, we know measurement of angle CBD is equal to 70 degrees. All right, each part of these is a different problem, so don't think they're the same. So the next one, they give us the opposite information. They tell us CBD is 100 degrees. Can we figure out what angle A is? Well, if when this was 35 and 35, this one was 70, then if this is 100, these must be what? What do you think they might be? So you could always work backwards. This would be 80 for supplementary. And if that's 80, then these must add up to 100, which has to be 50 and 50, because these are isosceles triangles. All right, so measurement of angle A is equal to 50 degrees. Alright, so if we don't, a more general answer, if measurement of angle A is x, let's say we don't know what it is, what is a measurement of CBD? Well, when this was 35, this one CBD was 70. When angle A was 50, CBD was 100. So the pattern seems to be that it's always going to be twice as big. So if angle A is x, then angle CBD is going to be 2x. Alright, so measurement of angle CBD is equal to 2x. Alright, so now we have a formula, really. So if we have a similar picture, I could give you any measurement for angle A, and you could tell me instantly what angle CBD is going to be without having to do a lot of work. Alright, so that's something good to have in your notes. Common test question that comes up. Again, go ahead and try to do the rest of these problems. They do review circles and systems of equations and a variety of other topics. Let me know if you have questions, and that's it for now. Thanks.